Hello, everybody, and welcome to week 2 of Data540. So this is really exciting. This week, we're jumping right into network models, which you can find in section 2.9 of the book. So, as section 2.9 would offer, certain models have a special structure that allows them to be solved using specialized algorithms, right? We're going to look at it by hand, but there are algorithms that can do this too. And that will relate to your discussion questions. So make sure you think about that as we're doing this. So one of the important classes of models is known as a network flow model, or sometimes it's just called a network model. And so the network is defined as a set of points, right? Sometimes those points are called V because they're known as vortices, or sometimes they're known as points N because they are also called nodes. We'll most often refer to them as nodes in this network model, right? So we're interested in the flow of the network model. So under the source item there on the left, you might call that item A, and you might call up top where it says flow equals path 1, you might call that item B. So you'd have node A at the source, node B at the top of this diamond, and in between that line would be known as an arc. Or if we called the destination C, the arc could be defined as AB or could be defined as ABC, right? Depending on what our goals are, right? And that arc is going to represent distance or time. That's going to become very important. That's what we're measuring and trying to maximize or minimize in this approach. So in the network, we're looking at the flow. And shortly, we're going to be talking about the shortest path. Now, the shortest path of a network model then, after moving from that short description in 2.9, you would jump to page 64, where it gives a good description of the shortest path model with a solid example, right? And it mentions that the path in the network is an ordered sequence of arcs, such that any node is visited at most once, right? And we're going to use that concept as we build our network and shortest path. And so our target should be paths which optimize performance. Optimize performance. And so system performance might be impacted by delays or throughput, right? The volume of traffic that you're trying to get through, the distance that the traffic has to go, various other nodes around the world. So think of as your IT traffic, your packets travel from router to router around the world, right? They get sent by the most direct route, or they get sent by the route that is most expeditious, right? That route could be through China, right? We don't know. It's what the router is choosing at the time based on congestion and routing tables and things like that. So, so this is what we're looking at. So why choose the shortest path at all? Well, partly the shortest path will often help us minimize costs. So think of a trucking route where you have deliveries, and you would want the shortest possible route. I think, though I'm not sure, one of the companies like FedEx, UPS, set up their route to maximize right turns. Because of the right turn on red, it makes the path faster because they can often just keep going. Sometimes you want to maximize system performance instead of prioritizing cost. But there's no guarantee that choosing the shortest path is going to maximize that performance. Things happen in life and in systems, right? So suppose the path weights lead to delays, right? There are Maybe it's 4 p.m. in a city where there's congestion. So even though you had all right turns planned, you weren't able to execute them, right? And so to do this well, all the connections would have to follow some sort of minimum weighted path, right? We want to make sure that it's fluid and flowing. Because overload and congestion um, are going to impact then the performance, right, and lead to overall delays. So we're going to talk quickly about network models, and we can do them manually or we can do them by algorithms. But in the end, the point is, are we going to maximize flow, minimize the cost, or are we going to look at shortest path, that sort of thing? So the shortest path determination can be done basically in one of three ways, is all I'm focusing on. It can be a logic path. It can be Dijkstra's algorithm, right, which is going to be useful. Or you could guess. Don't recommend guessing, but it can work many times, right? I posted a YouTube video, which I really like, in the additional material of this week, and it's only about 10 minutes long, and I wish you would listen to it. It talks about these three approaches. And you, next week, are going to apply the math of a shortest path in a problem. So please review that and make some notes. Ask any questions along the way. Now, so the focus right now is on the shortest path. But sometimes, dun dun dun, sometimes, right, we were choosing, remember we were talking about choosing the shortest path amongst all the given paths, but sometimes that is not always the best option. Sometimes we worried about unreliability, right? Like in IT, we have these packets flowing through the network, and the routers are routing these packets all over the world. And so we're concerned about packet loss. We might be concerned about the expenses. We might be concerned about security. So, for example, MPLS, I know you don't need to know this. This is just background or to fill in some of the gaps. But MPLS is a multi-protocol label switching system, right? It's very expensive. But data, when you have purchased MPLS capability in your company, it's data forwarding technology, and what it's going to do is increase the speed and control the flow of the network traffic. So with MPLS, data is directed through a path via labels instead of requiring the complex lookup tables in a routing table at every single router that it stops at. So normally a packet will hit a router will pull up its routing table, see where it should go, make sure that path is clear, and then send it on, right? MPLS is going to boom, 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 and skip all of that, right? But it's expensive. Another example might be a pack file, right? So a pack file is a proxy auto configuration, right? And it's a file that is a JavaScript function. Again, all this is just background. And what it's determining is whether the web browser requests, right? Your web browsers, it's collecting requests from HTTP or HTTPS if it's secure, or file transfer protocol, for example. And they go directly to the destination. So the pack file is determining whether that request goes right to the destination or if it should instead be forwarded to some sort of web proxy server. So a pack file, that proxy auto configuration, that's a text file that's going to have instructions that a browser uses to forward traffic to a proxy server. So instead of directly to the destination server, you might do that for security purposes, for example. And so browsers require the address of the pack file so that they can fetch the file from the specified address and execute the JavaScript in the file. Those are just some examples of how we're looking for the shortest path, but there are other considerations, right? We sometimes impose conditions that a session, which would be a session between you and your browser and your web server, they need to transmit traffic through some pre-selected paths, right? and they can split the traffic through all of them are some considerations, right? So there are many types of paths, sessions, and solutions. So, for example, three sessions between the source and the destination here are possible. There's the arc from the source node to path 1 to destination, or the arc from source to path 2 to destination, or it could be either, right, is another set of considerations. So IT uses largely often pre-selected paths, right, in these given sessions, right? And so routing decisions of our packets are needed for splitting the traffic, right? Which packet to send along which pack, and we're making routing decisions, right? Because we're using the network and flow to create the shortest path. So really these are scheduling decisions, and scheduling is very important because I'm going to go through a lengthy example of it in a minute of how that would work mathematically. So scheduling decisions are needed to decide the service order of the packets, right? And the objective is to maximize the system performance, right? And keep in mind, there are other factors, right? Throughput, if I allow too much throughput, I may have just allowed a DDoS attack, right? A directed denial of service, which is going to confuse a server and essentially allow some sort of buffer overflow in the memory, which gives a hacker or a bad person the ability to sometimes assume administrative privileges, right? Escalated privileges, which they can then do bad things to your server, your data, your company, etc. So the flow again matters in these regards, right? So we're talking about routing policy along the way. And so in general, another consideration is latency, right? As a customer, this is a primary concern. Whenever I'm managing computers, I want a positive customer experience. You do too. You click on a link, you want a response, right? And that comes down to the packet path. When a packet comes, we want to route it along the least congested path, right? And so, because remember, these servers, whether you have data loss prevention or antivirus, they're stopping your packet, opening it up, looking inside for errors, issues, viruses, closing it back up, and moving it on. There's a lot going on. And so congestion in a path can depend on the number of packets waiting for some service like that along the nodes, right? And so this is just another example of about when a packet comes, it'll decide which path to take. And the bottom line is that a packet at the bottom arriving at a certain time is going to be routed to the favored route, right, to keep it going in general. So we want to have a routing policy. When a packet comes, we route it along that least congested path, and the congestion in a path is going to depend on many factors, including the number of packets waiting along the nodes, right? This says really something similar. So what we want to do then is we're concerned also about the queuing length, right? Or the source node, right? And so when we're scheduling in IT, for example, we would be concerned about the service order of the packs, how many sessions are going on that are traversing this route or network or tree, which packet of the session should be served, etc., right? And so there's a difference of a backlog session scheduling. This really gets into IT. Not needed for today, but it's just background, and I think the slide is self-explanatory. What I want to get to is don't forget all the assumptions we're making about mobility, about other constraints, about packet losses and security. What about electromagnetic interference and other things that can happen, whether it's wired or wireless? Because what you're trying to do is take all of this, determine your resources, apply technologies. You would use this networking, this flow, these nodes, the shortest path to maybe someday deliver electricity. Okay, I'm going to stop there. Then we're going to come back with a PM example.